All right, let's solve the same problem with dynamics. Okay, dynamics means using F equals ma, right? Okay, so here's this marble on this incline. Oh, look at that. That's so good. All right, and then we know that this side is 0.56 long, right? That's the height of this triangle, right? And then we know that this side is 2.60 meters, right? This is going to be very handy, right? Because this angle right there is that the sine of that angle is just opposite over hypotenuse. So it'll be 0.56. We'll use that later, right? The sine of that theta is equal to 0.56 over 2.6. Okay, so we actually don't even have to calculate what the angle is and then take the sine of it. The sine just is 0.56 over 2.6, right? All right, so let's set this up, right? As this marble, and this, as this is, right, because it's 2/5 mr squared. As the marble rolls down this plane, there's a component of gravity, mg sine theta, acting down the plane, right? And so we've got mg sine theta is the force, right? And then that has to cause a linear acceleration of the marble, and then it also has to cause a rotational acceleration of the marble, right? So remember that what torque is Rf, right? Torque is also equal to I alpha, right? So if I want to get F, I just take this I alpha and divide by R, and I've got F, right? So the force needed, the tangential force needed to make this thing accelerate rotationally, right? And this is why things will roll down a plane faster than they would slide without friction, which is interesting. Okay, just simply because you have to rotationally accelerate it as well. So I alpha over R. And now we can substitute, right? So we get ma plus, and then we know that the moment of inertia is 2/5 mr squared. I'm using the moment of inertia we're given. Alpha is just a over r, right? Isn't that right? Let's see, a is alpha r, right? So alpha would be a over r, yes. All right, and then we divide that by r. Right, so now we've got, what do we got? We got mg sine theta is equal to ma plus, what do we got here? Okay, let's look at what happens. R cancels R. And then we have one R left, and that cancels this guy. And so it's ma plus 2/5 ma. Right. So it's ma amount to accelerated translationally, and then it's 2/5 of ma, right? It's a little easier to rotate it than to translate it, which is interesting. All right, let's see. So this would be 5/5. So that ultimately is 7/5 ma. And then I can cancel an m, and I get that A is 5/7 g sine theta, right? Now it even gets better than that, right? Because remember, sine theta is sine. Remember SOHCAHTOA, right? Sine is opposite over hypotenuse, right? So here's our opposite side. Here's our hypotenuse, right? And so it's just literally 0.56 over 2.6, right? So that equals 5/7 times 9.81, and then sine of theta is just 0.56. That's a lot to remember, right? I think this way is harder, but some people like this, you know. There it is. Okay, so what do we got? Let's figure this out. Hopefully we'll get this number after all that, right? Okay, so 5 divided by 7, how sad would it be, times 9.81 times 0.56 divided by 2.6. Oh, look at that. I get 1.5092 meters per second squared is our acceleration down the plane, right? Now we filled the space with so much stuff. So then it says, what's the final velocity at the bottom of the plane, right? We only have this much space to work with, right? Can we do it? Yeah, we can. Okay, so v squared is u squared plus 2as, right? So v will be the square root of 2 times 1.5092. And then the plane is 2.6 meters long, right? Here it comes, man. Square root of, we got the square root going, 2 times, the answer I just got, the 1.509 times 2.6. And that's 2.801 meters per second. Ta-da. So yeah, basically, you gotta remember this whole thing. This thing here, right? Can you remember that? Can you remember this trick? I mean, if you forget the trick, you could find the angle and then find the sine of the angle, right? I don't know. Is it